Okay, well, thanks for your patience. The I'm Mark Marley. I'm the director of the Lunar and Planetary Laboratory. Thank you so much for joining us, both online and here in person, for our fall, the first lecture of our fall evening lecture series. There's going to be 3 lectures tonight, and also we're going to have one on October 16th from Professor Jeff Andrews Hanna, and one on November 20th from research faculty member Angela Marusiak, talking about different aspects of lunar exploration. For those of you who are students and you need homework stamps, the extra credit, you can get those on your way out this evening. And then also stick around at the end. We'll have a lecture and then a Q&A, and then we'll have a raffle to give away some LPL and lunar themed items. So definitely stay around for that. The Lunar and Planetary Lab was founded in the early 1960s by Gerard Kuiper, who came to Arizona to establish the first academic department anywhere to really focus solely on the study of the planets, small bodies, moons of our solar system. And he called it the Lunar and Planetary Laboratory. And as I like to, or LPL, and as I like to say, the first L at LPL is lunar, for the study of the moon. Because a big focus of the early research here was to support NASA's Apollo missions to the moon and prepare for human landings on the moon. If you look outside, when you go out to your right, are some images from what was called the rectified lunar atlas. Because if you think about it, nothing had orbited the moon yet, and yet NASA was planning to go and send astronauts to land on the moon, and so they needed maps of the moon. And so one of the first projects here was to take high-resolution images with telescopes and then use those images to create maps that could be used for the planning of the lunar landings. And so that was all early 1960s, mid 1960s, so 60 years ago. And now, 60 years later, we have a whole new generation of scientists that are studying the moon and helping NASA once again to prepare for the return to the moon as NASA prepares to send humans again back to the moon. Our speaker tonight, who is emblematic of that theme of a new generation studying the moon, is Professor Jess Barnes. Dr. Barnes received her bachelor's degree in geosciences from the University of St. Andrews in Scotland, and her PhD in planetary and space sciences from the Open University and Natural History Museum of London in 2015. She went on to a series of postdoctoral appointments after that, including working as a NASA postdoctoral fellow at the NASA's Johnson Space Center in Houston. She joined us in LPL in 2020, just in time for COVID, and is trying to get her lab together and teaching during the early years of COVID. And she did a great job with that. And in fact, in 2019, she was Nature magazine named Jess as one of the 5 researchers shaking up lunar exploration. In 2020, she received the NASA Planetary Science Early Career Award for recognizing outstanding young scientists. And in 2023, she won the Near Prize from the Meteoritical Society. We're going to hear about her work tonight on a variety of topics, particularly on getting new insight from lunar samples 5 decades later. But in addition to all of her lunar science, Dr. Barnes works on meteorites from asteroids, samples from asteroids, the Bennu sample returned by the OSIRIS-REx mission, and meteorites that come from Mars. So she's an outstanding scientist, a great member of the LPL community, and please welcome Dr. Barnes for her lecture on new insights from old lunar samples.
You hear me online? Everyone hear me? Yeah? Of course, I forgot to put this on while I was having other snafus with the technology. Well, thank you very much, everyone. As Mark said, I joined LPL in the fall of 2019, and I actually gave the only other evening lecture that I've given before on September 18th, 2019. So exactly 5 years tonight. So on this project, but then we didn't have any results. So you're lucky because tonight you'll actually hear some results instead of me telling you what we were going to do or planning to do. Okay. So I really like this image. It's taken from Apollo 17, and it's an image of Earthrise from the Apollo 17 crew capsule. And tonight I'm going to be talking a lot about Apollo 17, so I thought this was pretty fitting. Oh, more tech issues. Not to worry, we can do it old school. Okay, so I'll give you a little overview of what we're going to be discussing tonight. So the whole theme around this project has been to understand better lunar volcanism. So on the moon, in the past, we've had volcanic activity. And so what that means is the interior of the moon partially melted, allowed magmas to rise to the surface, and those erupted onto the surface of the moon. Not quite like how we have volcanoes in Hawaii. They're not big cone-shaped structures, but allowing lavas to flow across the lunar surface. And so a lot of this work is all about better understanding how that volcanism worked, when it worked, and what the chemistry of those erupted lavas were. And we've done this through a program called the Apollo Next Generation Sample Analysis Program, or ANGSA, and I'll explain what that is, and then talk to you about this specific set of Apollo 17 volcanic samples, or basalts, that have been the focus of our study. Okay, so let's dive straight into lunar volcanism. So on the moon, maybe I should go back one slide so that you can see the moon again. Let's start here. So you look at the moon most nights and you'll see something that looks like this. You'll see the lunar surface is a mixture of gray colors. That doesn't mean it's boring. It's not. It's beautiful in its grayscale. But what you see are several things. You see different colors of gray, and those really represent different rock types, broadly speaking. We have the lunar highlands that are the bright colors, the whites, covering most of the southern hemisphere. And if we were to look at the far side of the moon that we can't see from Earth, that would be mostly this lighter color. And then you see these big basins and craters that are filled with this darker material. And that's where all the lavas are, or most of the lavas, most of the volcanic products on the surface of the moon. In more detail, we call those lavas mare basalt. So basalt describes the chemistry of those rocks, and mare because the craters filled with these lavas that I just showed you on the previous slide, the Latin for sea is mare, and so that's why they're called mare basalts. When we look at spectroscopic data from the surface of the moon taken by Lunar Prospector mission, we see that there are compositional differences across the lunar surface. So I just talked in color and more broadly. If you look at these images, you see that on the near side, so that's the side facing us, we see in these areas where we have these lavas, compositional hotspots for specific elements. So you can see the scale on the side of this graph here. We've got thorium, iron, and then if I move out of the way, titanium. So you can see that there are pieces of the front side or near side of the moon that are enriched in these elements. And that happens to be where the mare basalts are. And so what you can see too is that these maps are not homogeneous. They show different chemical compositions among these lavas. And so compositionally, the mare basalts expand a huge range of compositions in titanium, potassium, and aluminium, as well as trace elements. And that tells us something important about the chemistry of the interior of the moon, since these are not necessarily pieces of the interior of the moon or mantle material, but they derive from it. So by proxy, we can understand about the part of the moon we can't see, which is the interior, by studying these types of samples, either remotely from data sets like the one shown here, or in the laboratory. The other thing is you notice that these are widespread. Okay, they're mostly dominating the near side of the moon, but they're pretty widespread across the lunar surface. The other thing is that this mare basalt volcanism, this volcanic activity, lasted for quite a long time. So what I'm showing here is a different view of the moon. We've stretched it out a little bit. And what you're seeing are areas where, from counting craters on the lunar surface, we've been able to determine the age of those volcanic flows on the surface. And so it might be hard to read because the scale is upside down or wrong way, but All the purples represent old ages. So some of these lavas we think are up to 4 billion years old. But you'll notice that they extend all the way through to the greens, the yellows, and the oranges, all the way through to about 1 billion years old. So we had volcanic activity on the moon for at least 3 billion years old, which is kind of hard to explain, but is also incredible because it means that the moon, it tells us something about the moon's geological evolution, not just chemically, but also through time, and tells us something about the overall evolution of our nearest neighbor. But we don't just know the ages of these volcanic deposits from remote sensing. We have samples that were brought back by several missions to the lunar surface where humans went, collected material, and brought them back from 1969 to 1972, so the Apollo missions. But we also have material from the Luna. There were 3 landed lunar missions that from the Soviets that also brought material back, as well as more recently, the Chinese Space Agency brought material back from the lunar near side, and just a few months ago, also the southern region, South Pole region of the moon. And so when we look at those Mare basalt samples from those collection of missions, and we look at their chemistry in the laboratory, and we measure their ages, we see that we get a similar story, kind of. We see that we have some really old samples that are compositionally high in aluminium and some trace elements. And those are dated to around 4 billion years old or a bit older. And remember that the Earth-Moon system formed about 4.5 billion years old. So these are incredibly old samples. We then go into this kind of orange field, which is the kind of main period of Mare volcanism, which occurred between about 3.8 and 2.8 billion years ago. We don't have that many samples in our sample collection that extend all the way back as far as the crater counting chronology for the lunar surface indicate. The youngest age we have is about 2 billion years old, and that was dated on a sample brought back by the Chinese Space Agency a few years ago. So when we look at these samples and the lunar surface in general, we're seeing the history of volcanic activity on the moon throughout through time. When we look at these samples in the laboratory and we look at very thin slices of these rocks under a microscope, we also see that in addition to composition, they're texturally very diverse. And that's important because that tells us or gives us indications as to how quickly these lavas cooled or how slowly. Also tells us a little bit about the chemistry and can tell us about what dissolved gases they might have had within them as well. And so what you're looking at are an array of different microscope images. The one I want to draw your attention to is the one on the bottom left, which hopefully you can see has these big spherical holes in them. And those are not artifacts of making the sections. They're actually preserving evidence that the lava from which that rock crystallized was very gas rich, which is important if we want to try to piece together how the moon lost volatile elements like carbon or hydrogen. And we'll come back to that a little bit later. Okay, one more thing before we finish our kind of introduction to lunar volcanism is that we have this beautiful context. We're able to look at the lunar surface with remote orbiters. We're able to look at it telescopically. We're able to look at samples. But what we don't yet have is proper geologic context for the volcanic rocks that we brought back by the Apollo missions. And what do I mean by that? If you're a geologist like myself and you want to go and study, I don't know, Hawaiian volcanoes, you can go to Hawaii. You can go and look at an outcrop, collect your sample, take pictures of where you took that sample from, and understand the context in which that piece of that outcrop or rock formation, understand where you got that from. We don't have that for the samples that we currently have in the Apollo collection. And that's because a lot of those samples were collected from the surface. And the surface of the moon has been churned up by impact events through billions of years of being exposed to the harsh environment of space and being impacted by asteroids and comets. And so we lack this geologic context, but we have some clues as to the types of lava flows that might have been producing these rocks through what we call rills on the surface. And so this is an example of, it's a lunar reconnaissance orbiter image on the top. That's showing you Hadley Rill. at the Apollo 15 site. And then what you're seeing below is an actual photograph taken from Apollo 15 where they're looking into the rill. And so this is essentially a collapsed lava tube on the surface of the moon. And so one thing we've been investigating is, well, are there new techniques available today that weren't available during the Apollo era that can actually help us understand the geologic context, not by going back to the moon, we'd love to do that, but by using the samples that we already have to understand that context. And one final thing, I forgot about this one in the intro, is this idea of volatiles. And this is where my passion and my research really lies. Volatile elements are really crucial. Things like water, carbon dioxide, carbon monoxide. They're really important because they affect the physical chemical processes that control the stabilities of minerals and melts. They control fluids, they control magma eruption processes. So how explosive is your magmatic eruption or lava eruption going to be? And they also transport economically important metals if we're thinking about Earth or maybe some asteroids. Water is also, of course, very important for astrobiological reasons and for trying to understand the origin of Earth. And so in a lot of the work that I do, I'm trying to understand the abundance, distribution, and source of lunar volatiles in order to help me better understand what their role was in these volcanic eruptions. Are they really driven by loss of these volatiles? You can think of it like the magma will have had these dissolved water and carbon monoxide in them at depth, but when they rise to the surface, they get saturated in these elements, and then those elements and molecules want to leave the system and go into the gas phase, and essentially the lava or the magma will degas those volatiles. So we want to try to piece back together what their importance would have been during those processes and what roles they played during the, if we go further back in time, the differentiation of the moon itself. And then, of course, piecing that together with the other work that I do, like Mark mentioned, looking at asteroids and also Martian samples, try to better understand the accretion of volatiles in the inner solar system. So where did the bioessential elements that eventually led to life on Earth, where did those elements come from and from what types of materials? And surely the same types of materials that impacted Earth to deliver those ingredients also impacted the moon. And so how can we use the moon to better understand Earth's history? So that's the background. And now I want to talk about this amazing program called the Apollo Next Generation Sample Analysis Program. I want to give a shout out to the curation staff at NASA's Johnson Space Center. So Andrea, Charisse, and Juliana, if we go from left to right. This program is truly not just next generation sample analysis by using new techniques. It's really bringing in the next generation of lunar scientists to analyze rocks that were collected more than 50 years ago, and they're still being studied today and revealing new things about the moon that wouldn't be possible if we didn't have investment in programs like this and also investment in technology to enable these new discoveries. So what is ANGSA? As I mentioned, it's the Apollo Next Generation Sample Analysis Program. And the goals of ANGSA are pretty clear: to maximize the science derived from samples returned by the Apollo program 50 years ago in preparation for going back to the moon with the Artemis program in the 2020s and beyond. And so this program was announced in 2018. It was a competed selection process. You had to write proposals, and NASA opened up to the community for the first time some samples that had been stored under special conditions. And so they gave us the opportunity to write proposals to work on some of these special samples that had never been studied before. And those included things like unopened core samples. So the astronauts literally augured into the lunar surface, sometimes a meter or more than a meter, maybe 2 meters deep, collected core samples. Those were sealed or unopened since they were brought back, and those were available. There was also one that was vacuum sealed on the moon, so potentially could retain some ices. They wouldn't be ices anymore because the sample wasn't stored frozen, but if it was vacuum sealed, they should have retained those gases inside the core. Some samples were stored frozen for 50 years and then others stored in helium. And so we proposed to study one of the frozen samples. I'll talk to you about that in a minute. But there were 9 other teams selected. And one of the cool things about this this program is that once everyone was selected, they said, okay, you're all selected, but you're all going to join together and make this mega consortium of over, I think it's at this point, over 150 scientists worldwide. And you're going to all work together to try and meet the goals of this program, which was pretty exciting. And I'll show you on the very last slide why that was particularly exciting, because there was one person on this team who'd actually been to the moon. Okay, so all of the samples that were chosen, NASA basically took our proposals, the ones that were selected, and said, okay, we're going to only focus on some of these special samples from Apollo 17. And so because that's the theme tonight, Apollo 17, I want to take us back there. And so we're going to fly there. So brace yourselves. We're going to fly there using Lunar Reconnaissance Orbiter data, a reconstruction of actually landing in the Taurus Littrow Valley on the near side of the moon. And then you're going to see the EVAs. So hopefully it plays. It's nice and slow at the beginning, and then it gets a bit faster. So here we're working our way down in between Mare Serenitatis, Mare Tranquillitatis, and we're going to go to this area called the Taurus Littrow Valley. We're going to go in here. Now you can see a nice overlay. And this is the valley itself here. You can see this mountain over here. You can see this light deposit here. And now we start to see the traverses where the Apollo 17 astronauts went. We've got Traverse 1 or EVA 1, EVA 2, which is the longest one, and number 3. And so this is nice context for the sample that we're going to talk about, because our samples were collected on the rim of this Steno-Apollo crater at Station 1 on the Apollo 17 mission. But the sample that everyone kind of joined together to work on was one of the unopened core samples, and that was actually taken from this light mantle deposit that we thought was an avalanche that happened on the moon, and actually that core sample actually sampled that avalanche deposit. So we're going to go to Station 1 now and talk about the Steno-Apollo crater basalts. And so, as I said, this sample set was collected at Apollo 17 Station 1A. You can see a photograph here. The yellow dashed line indicates the rim of that Steno-Apollo crater. And this boulder, propped up nicely, is where 4 samples that we'll be talking about were collected. So 3 were collected from the right-hand side and 1 collected from the left-hand side of this boulder, and they were literally hacked off. You can go online and watch the video of, I think it was Jack Schmidt, hitting this boulder and trying to release samples from it. It's pretty entertaining. Of those 4 samples, they were all brought back to Earth. They're given these 7, 1, 0, 3, 5 type numbers, 5 digits. 7 represents Apollo 17. 1 is Station 1, and then this is the 35th sample that was collected. And so of these 4 samples, 1 was chosen to be frozen and kept frozen in special storage. And that was 71036 that you can see was collected from the right side of this boulder. And it was stored at minus 20 degrees Celsius until from 1972 all the way through to 2022. So I mentioned before that I gave this talk in 2019. It took us a while to get the samples because there was a little thing called a pandemic that happened in the middle, but that's for another day. All the other samples, so 71035, 37, and 55, were stored under what we call nominal curation conditions. So room temperature and pressure, but stored under nitrogen so they don't interact with Earth's atmosphere. They don't interact with water in the atmosphere. Okay, and so here are a list of questions that we're going to go through some data that we hope we can address these questions with. So we want to understand from this boulder, we want to understand if all of these samples, they were collected from a boulder, but we don't know the context of that boulder. It surely was not deposited, a lava flow does not deposit vertically, and so we know that this is not the orientation this boulder was in. It also is right beside a crater, so likely it was deposited there from somewhere else. So we want to understand, are all these samples the same? Are they chemically and mineralogically the same? How old are they? Because we don't know that yet. What was their eruptive and cooling histories when they were erupted onto the surface? Do they preserve any evidence for this degassing process that I talked about before, where volatile elements exsolve from the melt and are lost? Well, in the vacuum of space, anything that's lost could recondense onto the solid surface that is formed when these rocks solidify. So do we see any vesicles filled with species that could have been lost during that process? Do these samples preserve any evidence of having lost hydrogen? Are they from the same flow? Is this boulder representing a piece of one flow? Are they multiple flows that would have been on the surface? And then more broadly, do we see any differences between the samples that were stored under nominal conditions and those that were stored frozen, the one that was stored frozen? And so we're going to walk through how we started to assess this for these samples. I really like this image, even though this is just a title slide, but this is 71055, and I like the way curation tried to mimic the angle of the sun when this rock was collected to try, it kind of gives it like a spooky feeling. But you can really see all these little holes, these vesicles. When I showed you the photomicrographs from the optical microscope and the circles, that's what they look like in the rock. So it's like these holes that were once filled with gases, and the holes are essentially what's left over. We don't have the gases anymore, but we have the remnant of them. And we can still learn a lot, and I'll show you later how we can still learn a lot from those holes that are left. Throughout the talk, I'm going to be highlighting the students that have been involved in this project. It's been one of the great things about doing this work, not only as someone who wasn't born during the Apollo missions, but also the ability to bring new folks on who are the next generation of lunar scientists. So Ong was involved in helping me prepare some of these samples. I won't go into the details, but we looked at thin slices of rock, so-called thin sections, slightly thicker sections. Oh, I think I have a picture. Just whiz through those. We also mounted some samples in metal, like you can see up here, some fragments of these basalts in metal, to try and measure the hydrogen isotopes and hydrogen content without having to worry about terrestrial contamination. And then we also looked at some chips. So NASA actually provided us pretty big chips of these samples to investigate in 3 dimensions, and then also to cut some of those up and look at them as well. Here are some beauty shots of some of these samples, and they might just look like rocks, but it's very rare that you get granted the opportunity to study lunar basalts at this scale. These are centimeter-sized pieces of lunar samples. And what you can see really nicely on the bottom left over here is the outline of one of these circular vesicles. If you look really closely, there's another one here. And if you look at this image up here, you can see one on the top there and there as well. So these are indirectly recording this volatile loss process as we erupt lavas to the surface of the moon. And we can also see the mineralogy. So the white crystals, those are plagioclase. The brown looking ones are pyroxene. The black are oxide minerals. And then this beautiful green over here, that's an olivine crystal. So I mentioned that we started this project or got awarded funding in 2019. We got some samples, the ambient samples, later in 2019, 2020, but we didn't get the frozen sample until 2022. And that's because of the pandemic, but also because NASA didn't know how to process frozen samples. So they had these stored in a freezer, but they didn't have anywhere clean enough to actually take them out and prepare them, because you want to do it in a clean environment so you don't contaminate the sample. And so they had to build a custom freezer. It was actually pretty small. The inside had a nitrogen-filled glove box. So this is a walk-in freezer. It's minus 20 degrees Celsius. That's why they're wearing hats, even though it's Houston and it was springtime. But the neat thing about this project was they let us go and process the sample with them. So graduate student Zoe Wilbur is here and here. She was actually there the day that they revealed our sample for the first time and actually split it. I turned up the next day after the party was over, but Zoe was there and got to experience it firsthand. And there's the sample 71036 in its glory. And then we'll see some more beauty shots coming up. So this is Jeremy Kent, the processor for the Lunar Lab, processing the sample. You can see them weighing it. You can see, again, pockmarked with all these beautiful vesicles and just really beautiful. So in this clean environment that's cold, he was able to split the sample and provide some pieces to us. We didn't get the whole sample, but we got some fairly large pieces of it for our study. Okay, so now we're going to move on to talk about the actual analyses. So we used an array of different instrumentation, both here and across the United States. We used lots of different instrumentation. Everything in yellow are instruments that we used, and then some of the other instruments are indicated without the yellow outline. Okay, so first the mineralogy. So these samples are pretty typical of what we see in other Apollo 17 basalts. They contain olivine, pyroxene, plagioclase, ilmenite, which is important because that gives the Apollo 17 rocks their high titanium content. That mineral is an iron titanium oxide, and so we call those types of basalts high titanium. You can see this false color X-ray map. Basically, we've taken different elemental maps from the electron microprobe, overlain them, given them a color for each element, and then mixed them. And so you can see here, for example, olivine is colored green and ilmenite are the bright pinks. And so one thing we wanted to do was look at the modal abundance of different minerals in these samples to see if they were similar to each other. And that's kind of what the bar graph is showing over here, that generally speaking, all of these samples have the same types of minerals and in roughly the same proportions. We also did the same thing in 3 dimensions using what's called an X-ray computed tomography instrument, which is essentially like an X-ray. It takes an X-ray of the sample, but it does that the entire way through the sample. It's kind of like, imagine your sample is a loaf of bread and it's a sliced loaf of bread. What you get back out are all the slices, and you have to combine them to make your loaf of bread. And what we'll see later on, you get in those original images you get back from XCT, you'll get black and white images. What we've done here, what Zoe's done as part of her thesis, is actually color the different minerals. So what you're going to see is into the rock, the different minerals that are there. What we saw before was in 2 dimensions. This is 3 dimensions. And the beauty is you can leave the sample in its original bag from curation and scan it that way without ever touching or breaking the sample. You can get this type of information. So we're going to play a little video. So we're seeing in 3 dimensions. In blue, you've got olivines and pyroxenes. In pink, ilmenite. And some of the yellows are things like iron sulfide. And what you can do with this type of data is actually take away what you don't want to look at and just look at what you do want to see. And so here we're only seeing the ilmenite crystals and how they interlock with each other. And we can play the same game and do modal abundance. So look at the proportions of different minerals. And basically the bottom line is that in 2 dimensions and 3 dimensions, the modal abundances of these minerals across all 4 samples, even though I'm just showing a few here, they're all very similar, meaning chemically and mineralogically, these samples are all the same. Now we're going to move on to talk about one mineral in particular, and that's apatite. It's a calcium phosphate mineral that's important because in lunar samples, they're pretty dry, generally speaking, but apatite is one of those minerals that can actually take in hydrogen, as well as other volatile elements into its crystal structure. And you can use that to inform on how much water is in the lunar mantle, for example. And when we do that, the bottom line is that we can use chemical analysis of this mineral to try to understand how much water might be in those apatite crystals. And so we did these analyses on the electron microprobe downstairs. You can see here the chemical formula. What we do is with the microprobe, we can measure the abundances of fluorine and chlorine, which also go into the same crystallographic site as hydroxyl, but we can't measure the hydroxyl with the electron microprobe. So we play some funny wizardry where we measure fluorine and chlorine and assume the site adds up to 1 and calculate the difference, and that difference gives us the water content, essentially. And so when we do that, we calculate that these samples might contain up to 0.5% water, which is actually a lot of water for these lunar rocks that for 50 years were thought to be dry and have no water in them. We started trying to measure the water content with a different type of machine, but ran into some instrument issues. But basically what I want to show with this slide, I think I'm running out of time, is we measured around 100 to 6,000 parts per million. So we measured about 0.5% water. So we confirmed what our kind of back of the envelope calculation was telling us from the electron microprobe. In 2 of the samples, the frozen sample and one of the companion samples, we actually measured those water contents. So the goal of doing this with the ion microprobe is actually to measure and quantify the water content and its isotopic composition. But in that analytical session, we weren't actually able to get the hydrogen isotope ratio. The water contents we did measure, though, are very comparable to what's been measured for other Mare basalts in the laboratory from studies that I've done previously or other people have done previously. And this graph is showing you the water content in log scale on the x-axis and the hydrogen isotope content on the y. And yes, it's a mess. And so there's a lot to tease out here. There are a lot of different processes at work. But what I'm just showing with the red bar is that the red bar is more or less consistent with this red cluster of points that fall at around 1,000 or less parts per million water. And so overall, these basalts that we're looking at have similar water contents and extend the range that has previously been seen for these types of materials in the past. I'm actually going to skip sulfur. I'll come back to that at the end. What I want to show are the ages. And this is one of the cool things. And I was actually on a telecon earlier with my colleague who's been doing the dating of these samples. And so now I can share a little bit more information than even I knew at 9 o'clock this morning. So one of the things we really wanted to do with this study was to do something that folks don't normally do, which is combine in situ mineralogy, chemistry with 3D studies of these samples and take it a bit further to look at the isotopic composition of volatiles in the sample that we just talked about in apatite, but also date the samples using the best techniques available. And so to do that, we use the uranium-lead system. So uranium has 2 isotopes, 235 and 238 uranium, that are both unstable. And they undergo radioactive decay to form lead isotopes. And so you measure in your sample in specific minerals, you measure the abundance of uranium and the different isotopes of lead, and you can back out and calculate the age of your sample. It's pretty neat. And so these analyses were done at UCLA, and we targeted lots of different minerals that are known to contain lead or once contained uranium. Oh. Okay. And so what you're looking at on the right side is a lead-lead isotope plot. And so the details are not super critical. All I want to show you is that we're looking at 207 lead versus 206 lead. 207 lead and 206 lead are each the daughter products of this radioactive decay process when uranium decays. And the 2 different uranium isotopes decay at different times, which is one way why this particular chronometer that we call it is particularly useful. What you're seeing here are all of these points with an oval around them. Those are all individual points. So we've gone to the sample in 2 dimensions and put an ion beam on the sample and extracted uranium and lead from that spot. And then we've measured the ratio of that uranium and lead. And here I'm just showing the lead-lead isotopes. And so each spot is an individual analysis. And here we're only focused on these 3 samples. So we don't have the data for the frozen sample in this plot. And they're color coded. So all the blue are 71055, the red 71037, and the purple 71035. And crucially, when you look at a plot like this, when all the results line up on a line, that line is how you can extract the age. It also tells us, because they all lie on the same line, that they all have the same age. And so we can calculate that these samples actually have a formation age, a crystallization age of 3.7 billion years ago. So they're really old lunar Mare basalt samples, right at the start of the main phase of Mare volcanism. What's interesting is that one sample, 71055, had been dated in the 1970s using a different geochronology system using rubidium strontium, also one of these systems where rubidium decays to strontium. but they only got an age of 3.5 billion years old. So there's a difference there of 200 million years in age. So our age is much older than the previous age. And so we think that that possibly indicates that our age is the crystallization age, and the younger rubidium strontium age is actually recording an impact event that happened at 3.5 billion years ago. And if you're interested later, we've also done some other isotopic work using noble gases that shows something similar, but I won't discuss that right now in this talk. So they all have the same age, and they appear to be from the same source. So what that means is when you look at the lead isotopes, you don't only get the age, but you can also understand the isotopic composition of the source material, meaning we understand the lead isotopic composition of the mantle from which these particular magmas and then lavas formed from. Okay, and now we're going to go back to some of the 3D work, and this is really pioneering stuff. Zoe, my graduate student, has really been leading this and has taken it on a whole new direction that I never imagined. So what you can see again here is a sample. This one's 71055. Again, you can see these vesicles, and I've told you before that these indicate or are indirect recorders of this degassing or loss of volatiles during eruption. And the morphology of those holes can actually tell you a lot about the conditions during the eruptions themselves. And they can also tell you about any processes that happened in the flow as these samples are crystallizing. So what I'm going to show you next, I've already shown you kind of a false colored rendering of one of these scans of a sample in 3D. What you're going to see now is the black and white version of one of our samples. And so you're going to see different gray scales, different minerals and different gray scales. Minerals that appear darker, those are less dense minerals. Ones that appear brighter are really high Z phases, so high atomic number, high density. And then you're going to hopefully see some of the vesicles too, as we scan through the sample. And of course, the clicker is not working. Oh. Okay, so this movie is really beautiful. And again, we're scanning through a sample, looking at the interior without ever opening it up. So you can see some of these beautiful vesicles, these bubbles that would have been in the lava. You can see all the bright white crystals. Those are our ilmenite crystals. And you can see the whole way through the sample, we have a similar type of mineralogy that's not really changing. And we have different, some of these void spaces are spherical, others are more tortuous or elongated. And so Zoe went in and studied those different vesicle shapes and sizes in 3D. So here what you're seeing is a different sample, same idea, same type of data set, except now you're seeing a mask of the outside of the sample in this gray color, and all the vesicles have been highlighted in purple. And so this really allows us then to go in and really study in detail the 3 dimensions, not only of the sample, but of all these void spaces, which who knew that holes could tell you so much about a sample? Because I certainly didn't before we started this project. And so from studying this vesicularity of the samples, this bubbliness of our samples, we're able to do a couple of things. So we're able to calculate how much of the rock is empty space. And interestingly, the lunar receiving lab photographs, so those old photographs from the 1960s and 70s of Apollo samples, a lot of people studied those photographs and estimated the volume percent of those void spaces. For these samples, except for the frozen one, the vesicles or the vesicularity have been estimated at 20 to 40% voids or holes, empty space in these samples. But actually studying the samples with this new technique in 3 dimensions, Zoe was actually able to show that it's much less, it's between about 5 and 12% of the sample. And so that really influences our understanding of, well, if it's 40%, you must have lost a lot of vapor from the original, a lot of dissolved species from the original lava. If it's only 10%, that really affects the eruption dynamics and what you need to drive that volcanic eruption. The other thing that we can do by looking at the shapes of these vesicles is understand the amount of shear. And we're not going to go into too much detail, but basically these samples show next to no shear, which means that they were cooling pretty quickly in the interior of a lava flow. Okay, so let's build a picture of what we've learned so far from these samples. That 71036 is the one that has not been studied before. It was the one that was frozen. The other samples have been available for 50 years, but remarkably, hardly anyone had studied them. So this is the first time we've put all four together to try to understand their combined history. So mineralogically, they're all very similar. They all show a similar range in bulk composition that we've been able to calculate from their mineral chemistries. They all host reduced sulfur, which I didn't really talk about. They all have the same age and probably come from the similar source in the interior. And they all likely come because they have similar vesicle abundances and modal mineralogies in 3 dimensions. They probably come from the same lava flow. They're probably all from the same lava flow. And this boulder happened to just be sampling one particular part of a much larger lava flow. Based on the work that Zoe's been doing, we can actually put that into context. So coming back to this idea of we don't have context for lunar volcanic samples, based on studies of terrestrial systems, we actually know or think we know what the stratigraphy, what it looks like when you cut into a terrestrial lava flow. We have a very fine-grained or quickly cooled top, a quickly cooled bottom. In the middle, in this upper crust of the lava flow, we'll typically have oscillations between very vesicular regions and more crystalline regions. So this is crystallinity on this side, this is vesicularity. And then you have this core, which is much more coarse grained. So the grain sizes of minerals that you will form will be much bigger. And so based on all this work, we can actually say where we think we are within the lava flow with these samples. And we think we're in this upper crust based on our analyses of the vesicles, the minerals, and then we can even say, when this lava flow would have formed. And then this discrepancy is pretty interesting with the rubidium strontium age for 71055, because it possibly tells us that the lava flow formed 3.76 billion years ago, but then it was likely disturbed or impacted by an impact event. And that caused some of potentially the rubidium and or strontium to be lost from the system, most likely the rubidium, meaning there was an impact disturbance age recorded by that system, but not by the uranium lead system. So let's go back to our questions that we posed at the beginning. So everything in green, we've pretty much done a good job of addressing. We know their chemistry, we know how old they are, we know a lot more about their eruption and crystallization histories than we did before. We can now conclude that they are all from the same lava flow on the moon. We have not seen any real differences yet between the frozen sample and the ambient samples, but we haven't done the hydrogen isotope analyses yet. And so that's really where hopefully we'll see some differences. I mentioned as well these vapor deposits and the hydrogen isotope compositions contributing to our understanding of hydrogen loss. Those two things are still in the works. So we have ongoing projects looking using an electron microscope to understand, and Angela's in the audience, to understand if there are any vapor deposits on these samples. For a long time, for a couple of years, we were studying these rock chips and not seeing very much. Seeing some cool things that we hadn't seen in 2 dimensions, like these beautiful phosphate crystals lacing ilmenite, probably forming in contact with the vapor that was once in the bubble that you don't see. It's kind of coming out at you, the void space. We also see some crystals that look like they've been eaten away. This crystal of pyroxene is injecting into one of these void spaces, and it does not look very happy at all. It looks like it's being corroded. And so that's telling us something about the composition of the vapor that was once in the bubble that is now just an empty space in our sample. And then I think it was about 6 months ago, we hit the jackpot, and we started to find these beautiful features like feathery textured minerals lacing some other phases within these void spaces. And these are rich in copper, sulfur, and we've seen some hints that maybe also zinc. And so these elements are all ringing bells with being some of the species that might have been degassing from these lavas based on other work that we've done in the past. And so what we're going to do is we're going to go in detail look at the structure, the crystal structure, microstructure, and composition of these very, delicate looking vapor deposits. And then finally, poor Zoe has been here as long as I have, and I've promised her that we will analyze apatites in lunar samples and analyze their water content and their hydrogen isotope composition. And for whatever reason, every time we go to measure a sample, something happens. We currently have her samples in the brand new nanosims downstairs. All of those samples we're planning to measure in the next month or so. And we're going to target these apatite crystals and put our ion beam on these grains and measure the hydrogen isotope composition and water content. So hopefully in another 5 years, no, I'm joking, Zoe's not going to be here that long, we will have some results, hopefully in the next few weeks, to kind of conclude our project. Okay, and I wanted to end with, this has been a really great experience, not just in patience, in waiting for a sample, because these samples have well been worth the wait, but it's been a great experience. Just after I gave the evening lecture in 2019, Zoe and I were able to go to Johnson Space Center and help the curators process the unopened core sample. And that was a remarkable experience, learning how long it takes to do those types of things in a clean room, working with a precious sample and all the documentation and photographs and notes you have to take. But more than that, it's been working with more senior colleagues in the community, but also a lot of young folk. And so here's a picture from one of the meetings where Zoe's right there and some of the other grad students. And in the middle is Jack Schmidt. So Jack Schmidt was one of the Apollo 17 astronauts who actually collected our sample and the core sample. And he's part of the science team for ANGSA. And so it's been really interesting working with an astronaut and actually getting their perspective on the samples that you're studying in the laboratory. So I just wanted to thank NASA for the funding for this amazing project, and of course all the students who without whom this work wouldn't exist, and of course for Jack and the other Apollo astronauts for bringing back the samples. And so if there's time, I'll answer some questions. Thank you very much. Any questions?
Any questions from the room? And if you have questions online, you can type them into the chat and then Amy can read them to us. So go ahead.
Great talk, Jess. Thank you. I was curious about some of the processes when you were writing these proposals for ANGSA, especially for some of these samples that maybe haven't really been opened or looked at, right? Like, I'm curious what the process is writing a proposal, and you're going to open up these cores, and who knows what could or might be in there. How is that like an additional challenge in writing the proposals, or what do you think?
So a challenge, yes, but also pretty prescriptive. So we were given a set of samples to choose from, and world's your oyster. What do you want to do on these samples, and how is it going to further NASA science? How is it going to further lunar science? And really, in the spirit of ANGSA, how are you going to bring new technologies to understand these samples? So for me, one of the neat things, and I'm glad we did it, was to say we don't just want to study the frozen one, we want to study the other three. If we had chosen just to study the frozen one, we would have done nothing for 3 years and then only got started in 2022. For people studying the core sample, we have other cores that are open and have been open since they were brought back. And so lessons learned from unpacking those samples in the 60s and 70s really paved the way for folks to write those proposals on the core. Yep. Thanks, Isaiah.
Might be a silly question, but what was chosen from the surface of the moon? If they'd chosen some other rocks, would there be a difference in the results?
So that's a great question. And these samples were chosen because they were on this prominent boulder at that sample site. There are other samples. And of course, there's lots of rocks that haven't been sampled. So you only know what you know when you bring the sample back. There's only so much the astronauts could have done during the Apollo missions to understand the materials they were bringing back and, you know, make choices about, do I bring this one back or another one? There are some fun stories of them actually going against NASA policy and what the flight crew or flight directors wanted them to do on the lunar surface, and actually go and collect samples they weren't supposed to and put them in their pockets. Like seatbelt rock was one that was collected. They stopped the lunar ranging vehicle, stopped it, grabbed a sample that they weren't supposed to, and kind of tucked it away. But now that we have samples back and we've studied in more detail than ever, those samples brought back plus the lunar surface, you know, our understanding of the moon is evolving. So we really need to go back. We need to go to places we've not been before, like the South Pole, and really bring back samples and see what the wider geology of the moon looks like from bringing back other rocks. So that's a really great question. Thank you.
You want to say a little bit about this, how the South Pole might be different? What's special about the South Pole?
Yeah, so the South Pole is really interesting for many reasons. The South Pole is really dominated by a huge impact crater called South Pole Aitken Basin, which we think formed about shortly after the moon formed. And really, we think would have punched a hole through the lunar mantle and possibly exposed some of that material as the basin rebounded. It was then subsequently impacted by many more impactors. And so there are multi generations of impact events into that basin that could have exposed more mantle material. So understanding the age, going to the South Pole Aitken Basin, picking up some samples that record the age of that basin, not only helps us to understand its actual age, its real absolute age, but also will help better constrain what we call the lunar crater counting curve, which is how we can take these orbital images of the moon and understand the ages of basalts on the surface, or understand how old a particular surface is relative to another one. And that curve, that calibration curve, is actually used across the solar system. So the better we pin down the moon, the better we understand Mars, the better we understand some of the other bodies in our solar system. So that's one reason. For me, I'm most excited about going to the South Pole to bring back ice and to understand what the composition of that ice is, and to understand what objects have been delivering volatile elements to the lunar surface since it solidified. So yeah, a couple of reasons to go to the South Pole. There's many, many more.
And that's where the Artemis missions, the first Artemis landing is going to be. Let's maybe take one question online. Do we have anything from online?
Online right now.
Okay, any one last question from the room? Well, let's thank Jess again for a great talk.
Thank you, everyone.